Well, welcome back to part 3 of the chemical reactions unit. In the last part of the unit, in part 2, we focused on a concept called conservation of mass. And the idea of conservation of mass is that all of the atoms that are present before a reaction starts still have to be present after the reaction is over. But there has been a rearrangement, which is why it looks like you have new stuff there. You do have new stuff, but the atoms that new stuff is made from were present in different substances in the reactants before the reaction happened. So one way to show that is by showing a balance of mass. That is, if we measure the grams of mass in the reactants and the grams of mass in the products, we have to get the same number on both sides of the equation. Well, there's another way to show this, and it's a little bit more common, and it's known as balancing an equation. So that's really the focus today. It's called balancing chemical equations. Okay, and the whole point of balancing, because there might be a point where you're doing one, you find it kind of difficult, and you think, oh, why do we have to do this? It's to show conservation of mass. And it's actually easier than dealing with grams of things, because in reality, you're not going to be doing things in the laboratory where you can measure the masses before and after. So this is really about the only way that we're going to have to practically demonstrate conservation of mass. So let me give you an example of a reaction that I think you could all kind of relate to, and that is how water can break into its two elements. Now, water is called H2O, and that's because it is made of an oxygen atom that is chemically bonded to two hydrogen atoms. Well, what happens when these water molecules break apart, and we do this actually by zapping it with electricity in a certain way, it's called electrolysis, we can generate hydrogen gas, kind of cool explosive gas. I wish we could do this in school. And hydrogen is interesting. Hydrogen atoms do not exist by themselves. Because they're very unstable, they've got that one outer electron, they always will covalently bond to another hydrogen atom nearby. So when we write hydrogen, we always write it as H2. That means two bonded hydrogen atoms. That also is true of oxygen. Oxygen atoms do not exist as singular atoms floating around. They always exist as pairs bonded together. So we call it O2. So this shows us the substances. This arrow represents the reaction itself. But I want to show you that there's an imbalance in the atoms here. Because if we count the atoms on the reactant side, we've got two hydrogen atoms here. We've got two hydrogen atoms there. That looks good. But we have one oxygen atom in this water molecule. But over here, we have two oxygen atoms. So if we kind of draw this, let's just represent the oxygen atom as a red circle. Put a little O on it. And then each hydrogen we'll draw as a little H. So that is a good model for what a water molecule would look like. And over here, the H's exist as a pair. And the oxygens also exist as a pair. Again, the difference here is these are bonded together. Okay? So if you just look at the representation in the picture, you see, wait a minute, something's not balanced here. We've got an imbalance in the red oxygen atoms. So I'm going to show you how we do this balancing process now. So when I give you equations to balance, I'll always put some lines in front of each reactant and each product. Okay? And that line is going to be where you will write what we call a coefficient, if necessary. Okay, a coefficient. So without anything written on those lines, the coefficient is understood to be 1. We don't ever write a 1, but we see it there sort of in our imagination. And so we're counting, that's why I've drawn one of each of the molecules here. One water, one hydrogen, and one oxygen molecule. Now again, I'm not talking about atoms. One molecule of hydrogen is actually made of 2 atoms, and one molecule of oxygen is also made of 2 atoms. Okay, so now I'm going to start the balancing process, and it really just does this. You look at each side, and you pick one of the elements, and you say, do I have the same number on both sides? So let's start with hydrogen. You see you have 2 on this side of the arrow, and you have 2 on this side. So the hydrogens are actually balanced as it is, but not the oxygens, because this side only has 1, but this side has 2. Okay? So what these coefficients do is they multiply the number of atoms represented. All right? So because right now we need to double the number of oxygen atoms on the reactant side compared to the product side, we do that by putting in a 2. Now I'm actually using pencil here because this is something that you kind of do trial and error, right? So pencil is very important. Pen gets a little messy. So now what I've done by putting a 2 there is I've represented 2 water molecules. So I'm going to actually draw another water molecule with its oxygen and its 2 hydrogens. And so that now is what I have represented on the reactant side. Okay? So the good thing is I now balance my oxygen atoms. I have 2 on this side and I have 2 on this side. But in the process of doing the oxygens right, now I messed up my hydrogens. This is very common. But this is also an easy one to fix because I have 4 on this side, 2 on this water and 2 on this water. Or up here in the equation you can say 2 times 2. See, I'm multiplying the subscript by the coefficient. 2 times 2, that's 4. How do I represent 4 on the product side? Well, I need another pair of hydrogens, like that. And so what I do in my equation is I put a 2 for a coefficient out in front of that. So now I've got 4 hydrogens on both sides, and I still have 2 oxygens on both sides. So actually, I have balanced this equation. Okay? So my coefficients here when I'm done are a 2 and a 2 and this understood but unwritten 1. Okay? On the homework, if I ever ask you to write what the coefficients are, you still have to write a 1 in because there's no way to write in a blank. And we put 0. We never think of this as a 0. Okay? So the coefficients are 2, 2, 1. All right? So now I have balanced that equation. Now we'll look at another one. Okay, so here is the equation that would describe the formation of table salt, what we call sodium chloride. Okay, so here's the arrow that represents the reaction. So if we start with the element sodium, that's Na, kind of a funny symbol, remember, and the element chlorine, and chlorine is another one that does not exist as a singular atom because it's too unstable. With those 7 outer electrons, it is so anxious to bond with something else. So it shares one of its outer electrons with another chlorine, and so it always forms chlorine molecules, Cl2. And sodium chloride, we've written this ionic formula before, that's NaCl. So just to be helpful here, let's represent this sodium atom as a red circle, and this chlorine molecule, again that's 2 Cl's bonded or stuck together chemically. All right. And then over here, an NaCl would be one of the reds bonded to one of the greens. Now, I know you probably don't have colors, but it might help if you have something that you can use to kind of distinguish this, because it's a little easier to pick out what's going on here. So again, we have a situation where we don't have balance. Now, sometimes you're lucky and you have balance when you write the equation, and then all your coefficients are just 1. But in this case, we have an imbalance of chlorine because there's 2 atoms on this side in the molecule of chlorine, but there's only 1 on this side in this compound, sodium chloride. So again, we have to double the amount that we have. This time we're doubling it on the product side. And so I'll take my pencil. All right? Remember what we're doing here. We're multiplying. When we write these coefficients, it's not adding, it's really multiplying. And so I've doubled the number of NaCl's over here. So I'm going to draw another one. After a while, you can do this, hopefully without all the drawing, because it does take a little bit more time. So now I've got 2 chlorines on this side. Remember, I'm looking to the left of the arrow, and 2 chlorines on this side, so that's good. But in balancing my chlorines, I've unbalanced my sodiums. But it's easy enough to fix because the sodium is here by itself. So I can do anything to this over here with this coefficient and not affect the chlorine at all. I have 2 here, but only 1 on this side. So I'm going to put a coefficient of 2 right there. I'm going to draw another. Now, I'm not going to draw these bonded together. 2 NAs mean 2 independent and unbonded sodium atoms. Okay, those can exist by themselves. It's not normal. Usually they're kind of near each other, but we still consider it just an Na. And so now I have 2 on each side, and I can call my coefficients 2, 1, 2. Okay, again, don't write the 1. You just understand that it's there. All right. So I'm going to do a couple more, but I'm going to do these a little quicker because I'm not going to draw diagrams. But if it helps you to draw the pictures, by all means, stop my video, draw your own pictures, and it'll help you see kind of what I'm doing with the formulas and the equation. Okay, so take a second to pause this and write down the equation that I have here. These aren't substances that you would know, but what's different here is I have 2 reactants and 2 products, right? So if you look at what happened here, it looks like nitrogen was kind of kicked out of this compound here and ends up completely on its own, nitrogen being another one that exists in pairs. And so instead of the oxygen being on its own like it was on the reactant side, now it's combined with hydrogen to make the familiar water. Okay? So as you do the balancing without pictures, you just go through each element that you find, each symbol, and you look at the reactant side and you look at the product side and you just ask, do I have the same number represented on each side? Okay, so starting with nitrogen, because that's the one I see first, I see 2 on this side here, and I go over to the other side of the arrow, and I see 2 on that side there. So we're actually good with our nitrogens. Then I go to my hydrogens. Hydrogen, I have 4 on this side, but I only have 2 over here, because there's none in this, and there's 2 here. So I need to double the amount that I have on the right side so that it balances over here. Again, we're not adding to, we're actually doubling what we have. I know you think, well, isn't that the same thing? But coefficients are not adders, they're multipliers, okay? So I double what I have here. So now I have 4 hydrogens on this side, which is good. But if I go back to nitrogen, notice I did not change my nitrogens. I still have 2 and 2, so that's good. So I just have 1 more element to go here. I have 2 oxygens on the reactant side, and on the right side of the arrow, and be careful here, it looks like you have 1, but remember, this coefficient is now considered a multiplier. It doubles everything that you see after it. So it doubles the H's, so we have 4 of them, and it doubles the O, so we have 2 of them, which is good, because we have 2 on the reactant side too, right? So that's all I need to do to balance this one. I have a 1, 1, 1, 2 set of coefficients, okay? And I just didn't write the 1. All right. Let's do one more. Might be getting the hang of it already. Let's see. How about, it's called iron oxide. Iron is the symbol Fe. Iron oxide has the formula Fe2O3. And we'll combine it with some carbon. And what will happen is the carbon will kick the iron out of that compound. So we're going to make iron be by itself. And then we have carbon combined with the oxygen. CO2, that's carbon dioxide. All right? So we know we've moved on to a different one. There we are. Okay, so let's start as we did before. Again, I'm using pencil because this is trial and error. And you'll see on this one why I also have an eraser ready. So I'm going to start with my iron, since it's the first symbol that I see. I have, in this compound here on the reactant side, I have 2 atoms represented. And over here on the other side of the arrow, I have just 1. So again, I need to double the iron atoms that are represented on the product side. So I'll do that by doubling my coefficient from 1 to 2. And so now I'm good with my irons. Let's go to my oxygens. I have 3 on this side, but I only have 2 on the product side. Now, I can't double or triple or quadruple this number and end up with 3, can I? Okay, so again, a little trial and error. You might say, well, if you double it, then you have 4 on this side, but you still only have 3 on this side. So what you got to think here, this is how your math teacher would have taught you, you need a multiple that has both 2 and 3 in it. Okay, so the only way to make this work is to get 6 oxygen atoms on both sides. And the way that's going to work, so I'm going to erase this. Oops. Errant mark with the pencil there. Let's not make a mess. So I'm going to have to triple the coefficient over here from 1 to 3. See how what I just represented here now is 6 oxygen atoms. And then I'm going to go over here and I'm going to double the coefficient there so that I also represent 6 oxygen atoms. 2 times 3 and 3 times 2 is the same number. Now if you notice what I did there, I just went back and I messed up the iron, the Fe that I had originally started with. So anytime you go back and change a coefficient, you have to kind of start over and double check that you didn't mess something else up. So let's look here. Now my iron is 2 times 2. Okay? 2 times 2. That's 4 irons, but right here I only have 2 represented. I'm going to erase that 2, and I'm going to double that coefficient from 2 to 4. So I have balanced my irons, my Fe's, with 4 on both sides. Now I'm going to check my oxygens. I think they're still good, but let's make sure. I have 2 times 3, or 6 on this side, and I have 3 times 2, or 6 on that side. So we're good there. Now how about my carbons? Right now I haven't touched this coefficient, so there's only 1 atom represented there. But on the right side of the arrow, I have 3 of these carbon dioxide molecules. So that means 3 times 1, or 3 carbon atoms here. So how do I get 3 on the reactant side? I just need to triple my coefficient from 1 up to 3. And so when we go through and we check all 3 different kinds of elements, my iron, my oxygen, and my carbon, they are now all balanced. Okay? And if it helps you to look at a picture of this, it probably would be worth your while. So our set of coefficients, again on my homework I have to have you type in the coefficients since I can't see it in person. We would write 2, 3, 4, 3. Okay? That's about one of the more complicated sets of coefficients that you're likely to find. Okay, at least here early on. I mean, you're not going to be expected to do much more than this in here. When you take a chemistry class in the future, I hope you do. It might be a little bit more interesting in some more advanced ones. Okay, so there's a look at balancing. Again, it's all about equality or equivalent numbers of atoms on each side of the arrow. A little bit of trial and error, and every equation is a little different. It's not like there's a one set method for doing it, but it comes with practice, and so that's why I'll have some practice for you. And usually when I sort of train people to do this, I have to listen to them kind of talk themselves through it, because there's lots of different places to make little mistakes. Okay, so all right, we're going to leave it there. I'll give you a chance to practice. Ask questions as always if you have them, and we'll see if we can work them out. Okay, thanks for watching.